All right. Hello everybody. We started a little later today because we had a neighbor that decided to mow lawn right across the street from us. So there was a lot of background hissing and moaning. Um, so I figured it would be more appropriate to just wait 15 minutes and hope that he is done. Um, he doesn't look to be done, but then again, I don't know how much of a cleanup he's doing. So for now, it's quiet. So for now, we're gonna try to do some statistics, and then if he starts moaning again, we can we can either pause, or I can try to dull down the mic, or any other thing in between. All right, so today we're gonna start talking about confidence intervals. I changed the lighting a little bit, so hopefully uh, this will help, or at least not be completely destructive to our discussions. Let me know if that works or doesn't work for you. You know, like, comment, subscribe, kind of thing. All right, so confidence intervals. Maybe one of those will actually work the way it's supposed to. Okay. Confidence intervals. So when we talk about confidence intervals, we're talking about a way to estimate population proportions. Well, proportions, population parameters. So we're talking about estimating population parameters. Think about it this way: if somebody asks you how tall is your brother, sister, sibling, right? What you're gonna do is you're gonna say, "Hey, they're about E tall," and by E tall they mean, well, somewhere here, right? How high is your average classmate? Well, they're about this tall. Are they exactly this tall on average? No, but it's somewhere here. There's a ballpark of some sort. So we want to estimate this ballpark from a sample statistic. So what we're going to do is we're going to take a sample, we're going to collect our statistics, and we're going to create an estimate, right, for um, for a population parameter. So why? Well, again, populations are large and bulky, so we don't want to deal with those. And on the other hand, samples don't reflect the population perfectly or exactly. So what we're doing is we're creating some kind of fork to catch them. All right. So let's look at proportions. And for proportions, we need the following aspects. Well, first of all, and we need a random sample. There's nothing we can do without a random sample. And again, look at to chapter 2 for what that is all about. Second one, since we're talking about proportions, we need to look at towards binomial, the basics of binomial. And the basics for binomial that we talked about already was we needed a fixed number of trials. We needed trials that were independent. What does mean independent? One doesn't affect the other. So success or failure of one trial doesn't affect the next one. A roll of dice is one of those easy examples, but not picking cards, because if you pick a card, the deck by itself will get smaller. Then you need two outcomes, and again we're talking success and failure. And then this is new, we need this. This will guarantee that the sample we take is big enough. So if we're talking about coin flips, where P equals Q equals 50%, you need minimum 10 flips. Right? So after 10 flips, you're going to start getting a sample that is sufficiently big for us to have a conversation about. Again, why? Well, because flipping heads 10 times in a row is really, really difficult. On the other hand, if we have a situation where the probability of success is 95% and the probability of failure is 5%, the minimum is n equal to 100. Why? Is because unless we run 100 trials, we might not see a failure, which means that for all sakes and purposes, it's all going to be all success. If it's all success, it's kind of hard to do anything with it, right? So we have to run enough trials, have a sample size big enough for either to show up, right? If P was 5% and Q was 95, again, same idea. So both of those need to be matched. So this is this. So I'm going to introduce a term called the point estimate. And point estimate is exactly what it sounds like. It's a single value used to approximate or estimate a population parameter. Again, we're still talking about proportions, so P we're going to define as population proportion of success. P hat, and again, not making this up, P hat is sample proportion of success. Q hat is sample proportion of failure. Sorry, just double checking my notes. Okay. So how do we get this? Well, if sample proportion of success, right? P hat, not TPP, it's not a TP with a P inside. It's a P hat, right? So a P hat is sample proportion of success, which means what? Well, which means we take the number of successes divided by number of trials. Right? That's the proportion of success, which is what? Which is x divided by n equals to p hat. So what's q hat? Well, q hat is a complement of p hat. So it's 1 minus p hat. But that also means that p hat plus q hat equals to 1. Right? That's another one. And this also means that q hat equals to 1 minus x over n, which is n minus x over n. Different ways. Right. I don't know if you can hear, the neighbor is back at it. I'm so proud of him. He's working so hard. All right, so let's consider the following. Imagine we have a magician. And this magician does some card tricks. So if you've never seen a magician do card tricks, YouTube is your friend. So we have this magician doing some card trick. And what we observe that after 280 attempts, he succeeds 123 times. So the question is, what's p hat for this? Well, p hat for this is 123 divided by 280, right? Because p hat is x divided by n. Our x is the number of successes, 123, and n is the number of trials, 280, which comes out to be about 44%. And question, is this number right? Yes. Is this number good? It's a common question asked by non-scientists and non-mathematicians of mathematicians and scientists. Is this good? Well, question, what do you mean is this good? This is the only number you have. So you don't know how good this is, right? It's good because this is what the calculation tells you, but it's not good or bad in the grand scheme of things. Usually somebody in the upper management or middle management or somebody who has the actual framework to judge goodness of numbers will tell you if this number is good or not. You don't know. 44% could really suck at a magic trick, right? 44% of the time they get it right. It's not very impressive. On the other hand, if it's an impossibly difficult trick, 44 sounds really cool, right? Same with doctors. We could have done this example with doctors. If it's 44% to cure sniffles or cooties, the doctor ain't very good. But on the other hand, if it's 44% to do a life-altering and saving procedure that everybody else fails, 44 sounds fantastic. So again, is this good? What? Right? It's the only number we have. And because this is the only number we have, this is the only number we have to go on to do anything with it. So this becomes the point estimate for magicians doing this card trick, because that's the only thing we have. Right. Which brings us to this revelation of sorts, is that we have no idea how accurate the point estimate is. We have no idea how good this is, because we have nothing to compare it to. We don't have a census. It's kind of like here, right here. This is where we are, and it's the only number you have. So assume everything is here, but just kind of leaves you wondering. Right. Well, so let's expand. I'm gonna collapse this a little bit. Let's collapse it like this. Right. So let's consider, if we have a confidence, something's making funny noises. If we have a confidence interval, what is it really? I mean, right, it's not a point, it's some kind of a space. So it is a range. Range of what? Well, range of numbers. Right? So we have a range, and this range is used to estimate a population parameter. Right? Again, we are no longer talking about, hey, the population parameter is here. What we are saying is that the population parameter is somewhere between those two. Could it be close to one edge? Sure, could be close to the other, but it's somewhere here. Again, do we know for a fact it's here? No. But this is kind of the approach is, hey, we're going to guesstimate here. Of course, it's not complete guesstimation, because what we are going to do is we're going to create a framework around it. Well, so what do we need? Well, we need a confidence level. Confidence level, right? So what is confidence level? Confidence level is a number or a way for us to describe how confident we are that when we said, hey, the population parameter is between those two, how confident we are that we actually got it right. Right? Because how sure are you that you got this right? So this is how confident you are, or you want to be, that the value of population parameter will be inside the range, right? Inside of this interval. How sure are you? Right? The example I came up with is, think about moving a piano. How sure are you if the piano is going to fit through the door? Right? If you want to be really, really sure, like 99% sure, the piano better be very small, the door better be very, very large. Right? Yeah, this marker is going to fit here. I'm 95% sure. I'm looking at this huge marker and I'm thinking, yeah, it's going to fit right in between. Right? But how about now? Will this marker fit between those two? How sure you want to be? I'm about 40% sure. Well, I'm glad you're 40% sure, because it doesn't fit, right? So this kind of idea that confidence level is going to start affecting our setup. All right, so confidence level has a symbol, and that's 1 minus alpha. That's, if you don't know what alpha looks like, it looks like a Jesus fish. Right, so this is 1 minus alpha, where alpha would be the complement of the confidence level. So side note, alpha is the complement. Now I also define in the future, I will, instead of confidence level, I will be using a CL, and instead of a confidence interval, I will be using CI. This way my lazy side can skip writing confidence every single time. All right. So now question is, what next? Well, what next? Well, how about we look at the most common confidence levels? The most common ones, the most common confidence levels, right? What are the most common confidence levels? Well, the most common confidence levels are 90%, 95, and 99, with 95 being the most used. So, for the sake of argument, what would be the alpha? What would be the complement of it? Well, the alpha for the first one would be 10%, 5%, and 1%. Okay, so far, so good. Alright, so what do we do next with it? Well, let's introduce the language first and then work from there. So the language will look like this. So that's what the language looks like. The 95% confidence interval is 0.38, one smaller than p, smaller than 0.497. That's what it looks like. Well, what does it mean? Well, it means, first of all, I don't know what population, and the parameter we're using is proportion. So proportion actually is, right? Because we have no idea how accurate our point estimate is going to be, but we are, right? You don't know, but I'm helping. So we are 95% sure or confident that it will lie between or inside of the range or interval between 0.381 and 0.497. This is what it means. It means I don't know, but I'm 95% sure it's going to be here. Alright, so let's talk about how we can get this. To talk about this, we need to introduce critical values. And critical values are, or the way we've been looking at critical values, or we start to look at critical values, will show up all through chapter 4 and chapter 5 and in the future chapters as well. So critical values are a big deal. And what is a critical value? A critical value is a z-score that separates the likely region from the unlikely, from the unlikely region. That's all it does. So it's a z-score that separates yeah, probably here, and no, probably not. And I'm going to draw a big picture so we can we know this shape already. So what do we have? Well, we have some confidence level defined as CL or 1 minus alpha, right? So we have this confidence level in the middle. Then we have this unlikely space. So this is the likely space on the graph, and then there's the unlikely space. Now, how big is the unlikely space? If the middle part, right, the red part, if the red part is 1 minus alpha, then those two pieces together, this plus this, must be alpha. If this is 1 minus alpha, then those two need to be alpha. This is symmetric, so if alpha is this plus this, then only one side of it is half of it, and that's alpha over 2, and that would mean this space is alpha over 2 as well. This is how big it is. Again, probability and areas, I usually write them above the axis, and then z-scores end up on the bottom. In the middle we do have a 0 because it's a standard normal, and then we have a critical value here, z alpha over 2, and another critical value here, alpha over 2. So this is how the basics of it look like. All right, let me pull up. We're gonna need this. All right, so let's do the following. Let's look at the 3 most common confidence levels, and right here we have those right here, and let's look what the critical values for that would be. So for the first one, 90%, we would have the confidence level in the middle at 90%, which means that whatever is sticking outside of it would be 10% altogether, right? So alpha equals to 10%. So this side and this side is half of that, so alpha over 2, so this is 0.005, and this is alpha over 2, 0.05. Right? All right, if this is here, so on the bottom we have z alpha over 2 and z alpha over 2. Now how big is negative z alpha over 2? Well, if we look up 5% on a z-score table, we should get this answer, right? Because z-score tables give the z-score attached to the area to the left. So we take our table, try to zoom in here. So we have this, and what we're looking for is, right? We're looking for 5%. So where is 5% on our table? Well, our 5% is right here, between those two values. Slightly smaller, slightly larger. Again, since it's one of those common, this is one of those common confidence levels, and we're going to use this a lot, we assign an extra decimal place. Otherwise we would just go for whichever one of those two numbers is closer. Right, so this is 1.6, so this is negative 1.6, 4 and a half, 5. How do we get the other one? Well, we could either look up 95%, right? 90 plus 5, 95%, and get this one. Or we could realize that this is a symmetric curve. If it's symmetric, then this is 1.645. Sorry. And we're done. All right, let's look at the next one. 0.95, 1 minus alpha, boom, boom. And so what do we have? Well, we have 5% split into 2, so alpha over 2 here is 0.025, and alpha over 2 is 0.025. And so we're looking for those two values attached to 2.5%. Well, where's 2.5%? 2.5% is right here. And that's negative 1.96. 0.96, and this is 1.96. And again, you need to be able to do this by hand, but for homework's sake, which will be dropping tonight or tomorrow for both chapter 3 and 4, you're more than welcome to use an online calculator, but you need to understand how to do it by hand. All right, and then the last one right here. This is 99. If this is 99, then this is alpha over 2 half a%, and this is alpha over 2 half of a%. And again, if we look up half a%, it's right here between those two numbers, which means that this is negative 2.575 and this is 2.575. And again, this is how you do it by hand. Easy enough? All right. So before we move on, I'm gonna leave this up here, this back here, and zoom out. Ooh. Okay. So before we move on, here's a fun exercise. Imagine you got a table like this. And if you guys want, I can post a copy of this in a PDF file. But something like this. You should be able to fill this out on your own, and you should be able to do it relatively quickly. So I'm gonna zoom in so you can pause the video if you're watching with me. So here it is. Can you fill this out? Pause, and then I will do it with you. So in 5, 4, 3, 2, 1, unpause. Welcome back. Let's try this. So first one, 5%. Well, if it's 5%, then alpha over 2 is 0.025, right? 2.5%. And if we look this up on the z-score table, right, if we look up 2.5% is right here. So that makes it 1.96. If our alpha is 5%, what is confidence level? Confidence level is 1 minus alpha. So this is 100 minus 5%, 95%. Done. Next one, 1.645. Well, 1.645. Let's take a look at our table, our z-score table. Your table, the one that I posted for you, might have a picture. This one doesn't. 1.645. 1.645 tells me that this is 95%. Hang on, 95%, but I thought 95% was 1.6. Well, hang on, this is 95%. Remember this picture? If this number is 95%, means this right here is 5%. If this is 95, then this is 5. So alpha over 2 is 5%, which means alpha is 10%, which means confidence level is 90%. Next one, if this is 0.5%, then this means it's 1%, which means that this ends up being 99%. And if we look up 0.5%, we're going to get right here, negative 2.575. So 2.575. Now there might be a question, why am I not doing negatives? Because this is z alpha over 2, this is negative z alpha over 2, so this negative number is equivalent to a negative z alpha over 2. So if I remove the negative from one side and the other, I get the other side. Right. And then the last one, this is 78, so this ends up being 22%. So this ends up being 11%. And if we look up 11%, which is 0.11, 0.11 is right here, between those two numbers. This one's closer. So this becomes 1.23. And that's how you do it. I'll move. All right. So that's this. By the way, for sake of sanity, you should be able to do this. For practice, I think doing about 10 of those will make you really fast about being able to do it. So just make a table like this, confidence alpha, alpha over 2, z alpha over 2, and just crash through some of those. Now again, it's rare for me to to give a confidence level that is different than one of those three, but the probability of me doing so is not zero, even though it's very low. So take it as you will. Let's get back to. Oh, too much. You guys don't need to see what's on my desk. It's a mess. Every Tuesday morning, I show up to that little closet of a room which I call my office, and I do this off the table, just so we have some space to talk about statistics. Alright, so now that we have a level of confidence we want, and we have a point estimate, right? We have a sample statistics as a point estimate. We should consider what can we else add to it. Well, if we have a point estimate and we have some kind of range, we need to add that error that we are so confident about, right? When we say somebody is ye high, we say, hey, this plus kind of this rocking motion of adding extra. And that in statistics is called a margin of error. Of course, the symbol for margin of error is E. That's kind of obvious. But the margin of error is the maximum distance of what? Well, we started talking about proportions, so let's go proportions of p hat and p, like the maximum distance, I should probably say between p hat and p, right? Between the sample statistics and the population parameter. Again, we don't know where this is. So we get some data and we say, hey, this here and the center should be somewhere around there. The way you can think about it is, imagine somewhere in the far side there is a target, right? Say you go out hunting and somewhere between the trees there is a deer. It's in the middle of the night. You're the only one that didn't bring night gear, and the only thing you can trace is where are all the bullets or arrows or spears flying. And if they're all flying somewhere here, where would you imagine the deer to be? Would you guess that the deer to be somewhere here, right? Or would you imagine the deer Christmas is coming, so let's make it Rudolph, right? Or would you imagine the deer or the center of deer to be somewhere here? Now, could the deer be a little bit off either way? Yeah, it could, but it's probably here. If everybody is shooting in this general direction, right, or pointing at this general direction, the deer is probably here. Now, could it be off? Sure, there could be a light breeze, all the arrows kind of shifted over or something, but right, you this is what you want. You want this concept of, I'm pretty sure we're all aiming at the same thing, right? If you point towards somebody in the crowd and say, hey, my best friend is that guy, Do you mean this one or the one to the outside, right? Could you pass me that marker? Which one, right? All of these markers kind of satisfy this general direction. Which one? Well, either one of those, right? Now we can always pick up this one because it's different. So if I'm poking it, but either one of those could be the option. Definitely not those. Most likely not those, right? Because we are 95% sure when you said this, you didn't mean this. You meant something from around here. All right. Making a mess. All right. So that's the maximum distance. All right. So for proportion, what is that? Well, that's the critical value. And critical value you get from how confident you want to be, right? The more confident you want to be, the bigger this critical value is going to be, the bigger the margin of error is going to be. Times something that would give you a hint on how the data is spread around, about the variation in the data, right? It's asking, this is going to tell you about how the data is spread around, right? If the data is spread around very widely, I need a wider margin of error. If the data is very closely grouped together, my margin of error is going to be a little smaller, right? So this is this. Well, so what do we need? Well, first of all, we're going to need a p hat, a q hat, and an n. But that's not always the case, because if we have p hat, we can get q hat, right? So q hat is not always the unnecessary part. If you have p hat, you can get q hat. Why? Because p hat plus q hat equals to 1, so we can always solve that. Second one is we might not always get p hat, we might get x. Why? Well, because x divided by n is p hat. So we definitely need to get n, and then you need either an x or a p hat, and you can work for it. Second thing what we need is we need some confidence level, right, which is 1 minus alpha. So we can get the critical value, z alpha over 2. And then the last one is, well, we need to put it all together. To make this. No, hang on. We need stuff. This is just the margin error. Where's the confidence interval? What is the interval? Interval is some kind of a range. Some kind of range which has this maximum distance. Which means that if the population proportion was somewhere here, it's going to be somewhere between two things. Well, maximum distance on one side and maximum distance on the other. So this is the confidence interval we actually want. Now, in real world, people usually use this one. So if you look at polls for the 2020 election, what you will see people saying, hey, Kamala Harris has 5% popularity or favorability or voter turnout or whatever she has. They will say 5%. Why do they say 5%? Well, they say 5% because they say 5%. P is 5%. It's not terribly precise, but it's very common, because they're saying, hey, somebody's popularity is 5%. What they mean to say is that their p hat is 5%, and their E is say 1% or some other number. But this piece of information is usually hidden. So when you have an announcement of, hey, support for Kamala Harris is 5%, there's going to be a little asterisk, and on the very bottom there's going to be fine print saying, hey, the sample size was X, Y big, and the margin of error was 1%, or it's within 1%, or the confidence level is something. They have to give you this information. Either it's on the actual slide, it's on the website, it's inside of a document. There has to be some information where the hell they got those numbers from, because saying that the population proportion is 5% only works if you ran the census. If you didn't run the census, you cannot say that the population proportion, the population parameter is 5%. What you can say is that the sample proportion is 5%, and then abstract the fact that there's a margin of error of 1%, either implied or explicitly stated somewhere, and some confidence level. So we see this a lot in real life. All right, so that's the basic. Now I prefer this over this. This is lazy. This actually I find this a lot neater, because it actually gives you both values, right? The lower and the upper side of the range. Okay, so let's look at an example. Let's look at our magician. And our magician had an N of 280 and a success rate of 23 out of that. And we want to construct a 95% confidence interval for P. Alright, step one, we need a P hat, Q hat, and N. Well, N we have 280. P hat we have because P hat equals to X over N, so 123 divided by 280, which comes out to be 4393. Now, see how I did round? Couple examples ago, we rounded it. No. Yeah, we rounded it to 44. The reason why I'm not rounding it, because now I'm gonna do more with this number, which means I need this. Again, P hat is the sample proportion. What else do we need? We need Q hat. Well, Q hat is 1 minus P hat, which comes out to be 0.5607. Alright, what do we need next? 2, we need a confidence level into a critical value. Well, our 1 minus alpha was 95%, which gives us a Z alpha over 2 of 1.96. Roll back the video about 15, no, maybe not, maybe 10 minutes. About 10 minutes back, you should see how we got this. And then 3, we need the E, so our E is Z alpha over 2 P hat times Q hat divided by N square root. So in our case, that's 1.96 times 0.4393 times 0.5607 divided by 280. Sorry. All right, so for those of you who let's go. For those of you who might want to figure out how to do it on a calculator. Can you see? I hope you can. Okay, stop moving, stop moving. All right. So what I would recommend doing is working from the middle. So 0.4393 times 0.607 equals, divide by 280, second square root, right, square root of the answer times 1.96. So our margin of error comes out to be 0.0581. Right? Again, I'm going to go 0.4393 times 0.5607. I can divide right away to 280. And that's all of it is under square root. If your calculator doesn't have some kind of an answer function or faster function, write this and try to get a lot of decimal places, because the moment you start rounding, this number is going to start looking slightly different. Then you take square root of whatever the answer was, and then you can multiply it times 1.96. Cool. Do we have another calculator? Right, this is a Casio, so this is slightly different. So 0.4393 times 0.5607 divided by 280 equals, cool, square root, boom, times 1.96. Cool. Right, again, 0.4393 times 0.5607 divided by 280 equal, square root equal times 1.96. Alright, cool. Let's see more of the desk. Whoa. Alright. So that's this. And then the last step, is p hat minus e smaller than p smaller than p hat plus e. So in our case, that's 0.4393 minus 0.0581 smaller than p smaller than 0.393 plus 0.0581, which comes out to be 0.3812 smaller than p smaller than 0.4974. I don't know where the population proportion of magicians getting this card trick is, but we are 95% sure that's somewhere between 38.1 and 49.7%. All right, so let's consider the following. can we alter the margin of error? The answer is yes, we can. We cannot really touch p hat and q hat because those values, those sample statistics, we get from the actual sample. So unless you're planning on dropping things from the surveys or lying about the data you collected, you cannot really touch this, but you can attach those two. If we take z alpha over 2 and we increase z alpha over 2, then our margin of error is going to increase, which means that the confidence interval is going to get wider. If we drop z alpha over 2, we also shrink the confidence interval. And what is z alpha over 2? Well, z alpha over 2 is really a critical value associated with the confidence level, which means that if we increase our confidence, we need a wider confidence interval. If we are okay being less confident, the confidence interval is going to shrink. That's one. Second one is the sample size. If you rapidly increase the sample size, you make it a lot bigger, our margin of error is going to shrink. On the other hand, if you take much smaller sample, the margin of error is going to increase, right? If I asked you what's the proportion of black and red markers here is, you pick one, your margin of error is huge. But if you pick a handful, your margin of error is going to be very, very small, eventually reaching zero. The moment n becomes n, the margin of error becomes zero. So the moment you run a census, there is no margin of error. Why? Well, because then there is no interval. You got the actual value. So this is kind of a note to think about. All right. How much more we want to do from this? Let's continue. So let's consider the following. What happens if we need to figure out how big n do we want? So finding the required sample size. And here again, this is my favorite sentence in this chapter. Given a margin of error, you can find the sample size n needed to get that margin of error. Translation to real world, given enough cocaine, you can find a drug dealer that will sell you enough cocaine. Kind of backwards, right? If you have some margin of error that you get from the sample, you can figure out how big of a sample you need to get that margin of error. Right, so given how many kids you want, you can find a partner to have that many kids. So it's like, what? All right. So let me explain. When we had our margin of error like this. We could algebraically convert this to that. Or in some textbook it's written as z alpha over 2 squared divided by e squared p hat q hat n equals that. What does it mean? Well, the sample size is the critical value divided by margin of error squared times the sample proportion of success. And here comes that lovely discussion of ours. How the hell are we going to get this? So let's see. Z alpha over 2, so the critical value, we can get that from 1 minus alpha, right? We can get it from the confidence. We can get it from the confidence level. And the confidence level we should have in the back of our heads, we should have the confidence level that we're going to use for the sample. What the hell is going on? My brilliant neighbor, let me tell you about this. My brilliant neighbor, elderly gentleman with grayish hair, decided that the way to clean his lawnmower is to hit it against the pavement, picking it up and hitting it against the pavement. The brains on that guy are through the roof. Very proud of it. Anyways, so we can get that from, right, the confidence level. We can get this. So that's, we could get this, right, by having some kind of external. Seriously, dude. All right. We could get the margin of error by, having a setup. Say, don't get more than 1% margin of error. Right, so that we can get E. So we check, square is easy. How the hell are we getting p hat? Well, p hat and q hat, you get from the sample. How do you get p hat and q hat from a sample that you didn't take yet because you haven't decided how big of a sample it is? What? So here's the skinny. The skinny on this, or the spark notes on this, say the following. You can get a p hat, q hat kind of setup from couple places. You could have historical data. Say you ran the survey last month. So you have a ballpark idea of where p hat and q hat should be. Right, you keep tabs on it. So one of those historical. The other one is you could have kind of a pre-survey. Of course, survey people are going to get upset and call and tell you that pre-survey is not the proper term, but you could run a short survey just to get idea of what's going on. Maybe 100, 200, 500, 5,000 responses before you do the actual big survey, just to get an idea of where p hat and q hat really is. So you could have those two. You could try guesstimating, but again, this is probably some version of those two, either previous experiences or some expertise. You could probably guesstimate where p hat and q is. And then comes the part where you're like, well, I have no idea, right? Kind of I have no idea what happened to my homework. My dog ate it. Right? It's this kind of setup where we have no clue what p hat and q hat is. And here comes the part. Imagine you were placed in front of a choice, and this choice is not life altering, but it's a choice you care about. And I gave you two scenarios. In one scenario, 95% success. You know for a fact you're going to succeed 95%. And again, it's something you care about. It's asking somebody out for a date, haggling at one of the swap meets or one of the little markets, winning a lottery. Do you do it? Yeah, well, we do it. 95% success rate, we care about it, it's not life altering, sure. How about if I tell you something has 5% of success? If something has 5% of success, saying, asking out somebody on a date, haggling at a market, winning some, office lottery thing, do you do it? It does cost you some work, but 5%, we don't do it because why the hell, this is kind of a setup. Again, if it's life altering, the whole thing goes out the window. But in this case, right, what's the worst case scenario? Well, the worst case scenario is if you have no clue what it is. And what's the worst case scenario? Well, worst case scenario is 50-50, right? If you have 50% success, do you do it? Don't you do it, right? It's kind of a situation where like, hey, it's a coin flip. Will this work? It's a coin flip. If it's 95% chance of working, yeah, let's do it. 5% chance, why bother? 50-50, right? So that's the kind of a common language approach. Now, mathematically, we can look at it the following. If we have a p hat and q hat, right, together they have to equal to 1. So let's see. If we had p hat at, say, 1%, and q hat would be 99, right? If p hat was, say, 10%, q hat would be 90. If p hat was 20, this would be 80, 30, this would be 70, 40, this would be 60, and 50, this would be 50. And you can see that this just flipped. And let's look at our formula. In our formula, we multiply this. So what I'm going to, so this was the basics check. Now I'm going to look at p hat times q hat. Well, if I look at p hat times q hat, what is this? This is 0.0099. So this is 1%. This, if you multiply this out, this is 9%. This is 16. This is 21. This is 24. This is 25. And this is back to 24, and so on. See this? The multiplication of p hat times q hat is maximum when p hat equals q hat equals 50%. Right here, this. If this is maximum, means for p hat equal q hat equal 0.5, and, right, because this is going to be biggest, this is going to be biggest, n is going to go, be maximum as well. Which means what? Which means that if we can historically or some kind of pre-survey figure out what p hat and q hat is, we're gonna use that. Otherwise, we're gonna assume the worst case scenario, and in a worst case scenario, p hat equals q hat, and both of them are 50%, and our n becomes that, which means our n becomes that. So if you don't know what p hat and q hat is, and you have no way to find out, you're going to take the worst case scenario, and the worst case scenario says test more rather than less. So our sample is going to be much, much bigger. Again, if you don't have a p hat and q hat, this is what you assume. Assume they're 50%. Why? Because that gives you the biggest sample you can take. Again, why do we even bother doing this calculation versus just saying, well, we were hoping to take 1,000 people sample, but let's take 50,000 people sample? Well, because each sample costs money. If you're running surveys of some sort, the price for those can range anywhere from, say, 25, 35 cents a survey to 50, 70 bucks a survey. There's a huge difference between running 1,000 surveys and 2,000 surveys or 10,000 surveys. It's a lot of money, right? If we're talking about 50 bucks a survey, 1,000 survey means $50,000. If we can cut this down to 800, right, and save us some money, that's a huge advantage. Again, why? Because we want these two values. We want some confidence level and we want some margin of error, right? We want the margin of error to be something specific. In politics, that's usually 1%. So we are forced to have 1% here. And then we want to be 95% sure or 99% sure. So this is kind of set up. So the only thing that can affect this is this. If we have some prehistoric data, great. Or worst case scenario. But we are not going to just run a large sample, because if we run it large but not large enough, that's waste of money, because then our E is bigger than we want it. If we run it too large, our E will be smaller than we wanted. Our confidence level is good, but then we wasted money. If you can get exactly what you want for $10, why would you spend 50 bucks on it? And it's wasteful. And well, take it from somebody who made that mistake before, where I ran a survey way bigger than I needed and I wasted some money. Nobody's going to be happy about it. Right. So let's look at an example. What example do we want to use? Let's look at percentage of people who use email. So construct a confidence interval at 95%. For proportion of people in United States that use email. Okay, great. We need some more information. So this is what we want to do. Construct this confidence interval. But here's the question. What does the sample size need to be to ensure a margin of error of 4%? And by saying 4%, I mean 4% or less, but 4% is where we're going to end. All right, so we said historical data. Well, let's see. 16.9% of people used email in 1997. Right, so what do we need? Well, we need to figure out n. We have p hat, and that's 0.169. We have q hat, right? Because q hat is 1 minus p hat, and that comes out to be 831. We have e, and this is important. It's 4%. Decimal places. Don't put a 4 there. It's 0.04. We have z alpha over 2, because at 95%, our critical value is 1.96. So our n equals to z alpha over 2 divided by e times p hat q hat. So in our case that will be 1.96 divided by 0.04 squared 0.169 0.831. I'm sloppy writing. So our n comes out to be 337.19. Is this the answer? If you said yes, if you're thinking yes, well, this is what you calculate. It's not the answer. Because this implies you have to take 337 people and 19% of a person. So what you're going to do? Bring a head and an arm? Addams Family style? You monster. So we have to round this up. If we round this down, our margin of error is going to be above 4%. And if you work with administrations that are sticklers for numbers, say the Pentagon or US military, you go even tiny notch above 4%, they're going to chew you out and you're going to lose the contract. On the other hand, if you ask one extra person and your margin of error just drops slightly below 4%, nobody's going to bat an eye. So we round up to a whole person. All right, so this is kind of a neat thing. Now here questions, how relevant is data from 1997? Maybe not. So what happens if we have no data for p hat? Right, we know nothing about email usage. We just landed and we have no clue what to do. Well, then our formula turns into worst case scenario, right? Turns into that. Worst case scenario, it's 50-50. Again, if we fill this whole thing out, we get 625, which means our n has to be 601. Imagine if this is a $10 a survey. The difference between this is almost $300. No, sorry, 300 people, so almost $3,000 if it's $10 a survey, right? It's a huge difference. So if you have any indication that seems to be reliable, again, this is probably not reliable, but right, this is the difference. Again, we have a large margin of error, so this kind of works. All right. Questions? Yeah. Oh, hang on, no questions. Nobody's watching me. I'm here all alone. I'm so lonely, so very lonely. I got nobody but statistics. Okay, let's do what can we do? Let's do one more problem. All right. So out of 1,300 applicants to a medical school, 900 got in. And here's the question. Find the best point estimate. Find the best point estimate. Well, what is the best point estimate? Well, we're asking about population proportion. So we need a sample proportion. So we need a p hat. Well, p hat is what? X divided by n. How much is x? 900 got in, 900 successes out of 1,300 trials. And that would end up being 69%. Is this the best one? It is the only one, right? If you have only, say, one brother, it's your best brother and your worst brother at the same time. All right, B, construct a 99% confidence interval. Well, okay, p hat we have, q hat we can calculate, because q hat is 1 minus p hat, so that comes out to be 3077. What else do we need? Now we need n, which is 1,300. What else do we need? We need z alpha over 2, and at 99% z alpha over, right, so this one minus alpha, at 99% z alpha over 2 is 2575. Then our e becomes 2.57. Oh, maybe I should write z alpha over 2 p hat q hat divided by n squared. So that's z times 0.06.923 times 0.3077 divided by 1,300 and a big squared. So our E turns out to be 0.033. So our confidence interval, which is p hat minus E smaller than p hat plus E, turns out to be 0.692 minus 0.033. So that's 593 smaller than p smaller than 0.7253. And do most people get into the medical school? Yes. What do you mean most? Well, at least more than 50%. Yes, more than 50%. Again, we are 99% sure. There's 1% chance that this sample was extraordinary. Because when we say most people, we mean the population. Out of the population, people applying to medical school, most will get in based on this sample. And we are only 99% sure. This is paramount not to forget that there's this 99% here. Cool. Let's see what we have more to cover. We're taking a break. Let's take a 5-minute break, and then when we come back, I'm gonna push into confidence intervals for means. See you in about 5 minutes. Oh, I'm not getting any younger, so let's roll. We're back. Yes, no, I'm still alone. Still alone. Alright, so let's look at this. We did the proportion, so let's look at the means. Estimating population means. Alright, this is going to be fast and dirty because the explanation that worked for proportions are also going to work for the means. So aside the fact the formulas are going to change a little, a lot of the core ideas are going to be the same. So first thing, random sample. And the reason why I repeat this because this tends to be a big issue. I don't know why people don't like random samples. 2, and this is one of those I'm gonna lie to you before I tell you the truth, is we need population standard deviation, sigma. Now, if we have population standard deviation sigma, we most likely do have population mean. The reason why we need this for now is because we don't have the tools to work without it. So this is one of those, yeah, we did the population census, we got the mean, then the standard deviation, then there was a flood, fire, meteors, and we lost that piece of paper that said the mean, but we kept the one which had the standard deviation. Who knows? So for now we just assume that sigma is known. Third one is we need a normally distributed population or a large sample. Right? So large sample or population normally distributed. One or the other. If we have both, great, but it doesn't do anything for us. Alright, so that's the basics. What else? I love scooters so much. We know that the point estimate right for population mean mu is x bar, right? Sample average is the point estimate for population average. Check. What else? Well, the margin of error. Again, when we're talking about margin of error, we're talking the maximum distance between the sample statistics and the population parameter. Well, in our case, that's no change here, still critical value, and then some indication on how the data is spread around. And that leaves us with what? Well, that leaves us with the confidence interval, and then the confidence interval is that. And that's it. So what do we need to do? Well, one is when we work on those problems, we need to check requirements. This. Do we have this? If we don't have this, this becomes an issue. 2, we need to get our 1 minus alpha and turn it into z alpha over 2. We need to take our confidence level and turn it into a critical value. 3, we need to find our E, which is that. And then 4, we need to actually build a confidence interval. So imagine we have couple students. So let's say we have a random sample of 40 students. By the way, guys, if you want extra problems for any of the sections we covered so far, just shoot me a message or post a question in the discussion saying, hey, teach confidence intervals for means mu, and I will generate you a set of problems which you can work with, because again, I don't know what you need, and until you tell me, I'm gonna just blatantly assume that I'm doing it the right way. Anyways, so random sample of 40 students. Let's assume that, let's measure their heart rate. So after we take a random sample of 40 students, their heart rate is 76.3 beats per minute. Right? We know population standard deviation is 12.5 beats per minute, and we want to construct a 99% confidence interval for average population heart rate. Well, let's see. Checking requirements. Random sample, check. Large sample, check. Do we have sigma? Yes, we do. 12.5. What else? We need to find critical value. Well, z alpha over 2 for 99% is 2.575. Check that. Well, we probably should write down the average, which is 76.3. So our E turns out to be z alpha over 2 sigma divided by square root of n. So that comes out to be 2.575 times a fraction that has 12.5 on top and a square root of 40 on the bottom. And that comes out to be 5.08. So the confidence interval, which is x bar minus e smaller than mu smaller than x bar plus e, turns out to be 76.3 minus 5.08 smaller than mu smaller than 76.3 plus 5.08, which 71.22 smaller than mu smaller than 81.38. We don't know exactly what the population average heart rate is, but we are 99% sure it's somewhere between 71.22 and 81.38 beats per minute. Yeah, same thing. All right, margin of error. So let's find the required sample size. Again, if our E was Z alpha over 2, sigma divided by square root of n, after some conversions, n becomes Z alpha over 2 sigma divided by E squared. So how about this? IQ scores have a standard deviation of 15. How large of a sample I need to take to how sample I need to take to be 95% sure it is within 2 points of population average, right? So if I take a sample and I take an average of the IQ scores of the sample, I want to be 95% sure that that sample is within 2 points of population average. So what do we have here? Well, first of all, we have Z alpha over 2, right? 95% will give us 1.96. We have sigma, that's 15, and we have E, right, within 2 points. The distance is 2. So our n equals to Z alpha over 2 sigma divided by E squared. Well, that's 1.96 times times 15 divided by 2 squared. That comes out to be 206.9. And again, 9% of a person is not good enough, so we round up. Cool, right? I think so. I think this is really cool. All right. Boom. Boom shakalaka. All right. So we're doing all right. So I'm feeling up for it. So what I'm going to do is I'm going to keep going. If well, apparently he wants to keep going too. And if 2 hours is about your limit of dealing with statistics, what I recommend to do is take a pause, go do other things, come back and then keep watching. I'm gonna keep on grinding because I'm feeling it today. So if you still here, hi. If you're not, well, see you soon. So what do we do about the mean if sigma is not known, right? In this little thing, we had this major thing here. We assumed sigma was known. What happens if it is known? Well, the problem is that if we don't know sigma, right, population standard deviation, we can't use the z-score. And this problem showed up at this really small, kind of nobody heard of it brewery called Guinness. And there was a guy there that wanted to do statistics on the beer. The problem is, to do statistics on the beer, he needed sigma. The problem of having sigma means population standard deviation, which means he had to open every bottle, every casket, everything. I don't know about you guys, but me personally, second-hand beer just doesn't sound very appetizing. So he needed to develop a way to test statements about the population of the beer, right? The population, all the caskets and beer bottles and whatnot, without testing every single bottle. And he developed it, and because Guinness, like any other big corporation, is very secretive about, the progress they make, and they are not playing nice with everybody, and they don't want to share, he submitted that paper and signed it Student T. And so nowadays, when we talk about his way of dealing with the lack of sigma, we call it a Student T score or Student T statistic. So instead of a z-score, we use a t-score. Alright, so what is a t-score? Well, for t-scores, we need the following. One, we need a random sample. That's the theme of this class, random samples. Two, we want a big sample or a sample from a population that is normally distributed. So we still want that normal distribution. Now, we used to have that the z-scores were calculated the following way. This is how we used to calculate. Well, now we're going to be calculating t-scores. And again, x bar and mu don't change. What changes is the standard deviation. We don't have population standard deviation, so what we have is the next best thing, which is a sample standard deviation. Okay, well, that changes a couple things. Critical values, for example, are no longer z alpha over 2, but are t alpha over 2. Are t alpha over 2. All right, so here's the problem. If we're not using z-scores, bye-bye goes standard normal distribution and z-scores. This whole thing that we just got used to using, we no longer use. But if you flip your table packet, you're going to get one of these tables, or if you look up a t table, you're going to get a set of t tables. And do we have a t table here? Oh, here it is. So there's several t tables available everywhere, and they all have a very common features. I'm going to zoom in so we can see that. Now, the tables I got for you are ones which have, a little bit more information on top. But the most standard and common one looks like this. Right? First of all, it only gives you positive values, assumes that you can figure out that the graph is symmetric, so the negative values on the other side. Second of all, it has some numbers on top, and then has a whole column called df. So first thing we need to figure out what the hell is that df. And df stands for degrees of freedom. Right? And what are degrees of freedom? Degrees of freedom are how many ways things can change. So the way to think of it is, imagine if you have 4 markers. How many choices do you have? Well, you have 4 choices, right? How about now? 3 choices. How about now? 2 choices. How about now? You want to say 1 choice, but you don't really have 1 choice. This is the last marker. This is the only thing that's left. So when you're looking at 4 markers, what you really have is a choice for the first one, choice for the second one, choice for the third one. The 4th marker doesn't get a choice. So the degrees of freedom as such are defined as n-1. Right? If you have 10 objects, you only make 9 choices because the 10th object is there. Think about it the way you would think about kids picking teams on the playground, right? If you're the last kid standing in line, you're not really a choice, right? If you're stranded in the middle of the ocean and there's only one other human being, well, that's going to be your best friend. It's kind of stuck, right? So that's what these degrees of freedom are. Now on top, what you have is you have the area of the graph that this t-score right here represents. Let me show you. Right. So let's say that for a sample size 23 from a normally distributed population, we want to find the critical value T alpha over 2 for a confidence level of 95%. Okay, well, so let's take a look. Well, if the middle part is 95%, how big are those alpha over 2's on both sides? Well, if this is 95%, right, this little section is 95%, then this and this together are 5%. So each one of those is 2.5%. Yes? Okay. So now we look at our table. Going back to, sorry guys, I'm going to be doing zooming out. So now what we're looking for is we're looking at 2.5% right here. Right here. And then our degrees of freedom, well, we had a sample size of 23. And degrees of freedom are n-1. So our degrees of freedom are equal to n-1, which is 23 minus 1, which is 22. Right? So we're looking at 2.5% at degrees of freedom of 22. So 2.5% at degrees of 22. which makes it 2.074. Which makes T alpha over 2 at 2.074. Right here. And that's how you find the critical value. Now, the table in your packet will have one tail, two tail, or confidence level available to you. So you have to be careful which one you pick and why. If it has a confidence level actually spelled out, then you can, right, confidence level actually spelled out, then you can just look up this. But a confidence level of 95 means that two tails together, right? So both of those are 5%, which means one tail is 2.5%, and then you go down and there's the number. Right. So this is how we find critical values. Well, if we have critical values, then we should have margin of error. Well, E nowadays is T alpha over 2 versus Z alpha over 2. And since we don't have sigma, we use S and then square root of N. Which makes the confidence interval, well, still the same. Just the way we calculate E changed a little. That's it. There's nothing more to it. Alright, let's try something. So we want to construct a 95% confidence interval for the average age of people. What do we want to do? Average age of people promoted to manager at some company. So if we take a sample of 23 people at this company, the average age of promotion was 47, with a standard deviation of 7.2. Right. Assume population of ages is normally distributed. Construct a 95% confidence interval for the average age of people promoted to manager. Sample of 23 people, right, in this company. The average age of promotion was 47, with a standard deviation of 7.2. Assume population is normally distributed. Alright, so let's see. What do we have? Well, we have N at 23. Which means that we have a degrees of freedom of 22. We have an X bar at 47. We have a sigma of wrong we don't have sigma. We have a sample with an average and a standard deviation, which means that we have S at 7.2. We have 1 minus alpha at 95, which means we have alpha at 0.05, right? Or if you prefer, alpha over 2 at 0.025, okay? Which means that we have T alpha over 2 at 2.074. How do I know that? Well, we just did this example, which means that our E is T alpha over 2 S divided by square root of N, which is 2.074 times 7.2 divided by square root of 23. That's N, that's not DF, so 23. And that comes out to be 3.1, which means that our confidence interval ends up being, well, it's being 47 minus 3.1, smaller than mu, smaller than 47 plus, I don't know why I keep on putting the dot there, 3.1. So that ends up being 43.9, smaller than mu, smaller than 50.1. We don't know what the average age of promotion to a manager at this company is, but we are 95% sure it's somewhere between 43.9 and 50.1 years of age. If you consider it, right, this. All right. Let's do one more. Nothing like ends like a good stream, like a crack baby. So let's consider the following. In a random sample of 90 babies born to cocaine using mothers, the average weight was 2,700 grams with a standard deviation of 645 grams. If you're wondering, about 450 grams is a pound. So for people that are actually curious about, so 450 grams is about 1 pound. So we're talking let's see. So we're talking about kids that are 6 pounds on average, small. Construct a 99% confidence interval for population for the population average weight or birth weight of those kids. Well, let's see. N equals to 90, right? So df will equal to 89. Mu equals, do we have mu? No, we don't have mu. This average is the sample average, so we have x bar equal to 2,700, right? We have S at 645. What else? We have 1 minus alpha at 0.99, which means that we have alpha at 0.01. Okay, well, let's take a look. I don't have an 89 on none of my tables. Now the table I have right now in front of me has a 90. But worst case scenario, this table has an 80 and 100. If you're confronted with this possibility, now it's unlikely on the final exam that I will toss you a curve like this. But if you're confronted with the possibility where you don't have 89 and you don't have access to a more detailed table, you don't have a computer program or a website or a calculator to run this, pick the one that is closer, but also mind that you want to pick a slightly smaller DF rather than slightly higher. It's better to overestimate than underestimate, right? So what we're going to do is we're going to look for T alpha over 2 for a DF of 80, because that's what the table I have gives me. And again, what am I looking for? I'm looking for alpha of 1, which means alpha over 2 is 0.005. Right? My table again gives me confidence level on the bottom and gives me some other things, 1 tail, 2 tail. So, but if I didn't have that, I'm looking at 0.5% in here. All right, so at 80 and 5, I got 2.639. If I used a little bit more detailed one, this will be 2.632, which means that those numbers are extremely close. Right, so we got our T alpha over 2. Then let's find our E. E is T alpha over 2 S divided by square root of N, which means that this is 2.639 645 divided by square root of 90. Here's another important part. As long as you show where you got things from, there's a really high probability you're going to get a lot of partial credit for it. So again, even if you don't have exactly what you're looking for, just write where you got it from, like this kind of example, and that's going to be okay to work with. And this comes out to be 179.42. 423. So our confidence interval comes out to be 2520.577, smaller than mu, smaller than 423. This is 2879.423. Again, I don't know what the population average weight of babies born to cocaine using mothers actually is, but I am 99% sure it's somewhere between 2520 and 2879. Actually, I'm going to rewrite those numbers bigger. And this is 2520 20.577 smaller than mu smaller than 2879 423. And that closes the confidence interval section. All right. What do we have next? Well, we have confidence intervals for population variation. I might do a separate low video for that later. And then we're on to chapter 5, which is hypothesis testing. So I think we're in a good shape. Expect chapter 3 and 4 homework to drop within the next 48 hours. I'm finishing testing some of the questions, making sure that they're, well, the numbers come out nice, and then there's going to be at least 2 weeks to complete that. If there's any questions, just send me an email, post a comment on the videos, post a comment in the discussion board or any other way, and we will take it from there. Again, for some reason, my office hours setup wasn't working. I reposted the link in the announcements, so if you guys want to catch me in my office hours as well, there's a way to do that. Again, have a great week and do more statistics. See you guys soon.